So the next thing is I talked about unit vectors, but let's formalize what vectors are. So in vector fields, we said that for every location x, y, z, or now r theta phi or r phi z, in whatever coordinate systems you may choose, I need to associate a vector for every location, right? So this vector also now requires three independent numbers, right? So I need three independent numbers to specify a location in three-dimensional space, and I also need three numbers to specify a vector, right? And a vector, in the most simplest case you can think of, is an arrow, right? Not a physical arrow, but you have to picture that you can sort of associate this vector as an arrow where it has both magnitude, which is represented by the length of the arrow, and a direction in which it is pointing towards. Okay, so vectors also need three parameters to specify magnitude, and direction. Right, and we can use any of the coordinate systems to do so, right? So usually at any point, let's say I take the rectangular coordinate system, I am going to a location x comma y comma z, I put the tail end, right, of the vector, I put the tail end of the vector at x comma y comma z, right, and then allow the direction and the magnitude to be specified by this arrow, right, where the head is pointing towards the direction in which the vector needs to be pointing, and the length of the arrow tells me the magnitude. Okay, so it is easy to draw vectors in the profile view, right? So when I hold the vector in front of me, I can certainly see its length, right, and I can see its direction in which it is pointed to. Now the trouble is, how do we represent in images on textbooks or papers when the vector is actually pointing towards you or away from you, right? So we have some nomenclature there. In order to specify both direction and magnitude, we have the frontal view, where we use a dot and a circle, right? So this is an arrow that is pointing at you, right? And in order to specify magnitude, again this is only a relative sense when we start drawing these pictures, but in order to show large to small magnitudes, we use relative sizes of these circles that we have drawn, right? So a bigger circle indicates higher magnitude, right, and an arrow that is pointing towards you, right? And then we have the back view as well, where we use a cross and a circle around the cross, and again, in order to indicate magnitude or strength, we just grow the size of the circle and the cross, right? So I'm going to take the rectangular coordinate system for most of our lecture this week because it's convenient, but you can also think that you can extend these to other coordinate systems, right? So in rectangular coordinate system, I can represent a vector A usually with a small arrow on the top, or some textbooks use the bold face, right? Can be written as A x times Ex okay. So I need three numbers Ax, Ay, Az that essentially tell me the information of the magnitude and direction, right? So the magnitude of this vector A is simply given by the square root of the sum of squares of the three components, right? Ex, Ey and Ez are unit vectors, right? So we are using vectors in order to create a generalized vector. The speciality of these Ex, Ey, Ez are they're all of unit magnitude. They only have a length of 1, right? Normalized to the, they don't have any units, right? So they are just normalized to a magnitude of 1. And Ax, Ay, Az are the triplets are real valued, right? So these unit vectors are essentially along the x, y and z axes, right? The rectangular coordinate system. So if I were to talk of a vector field, now each of these x, Ax, Ay, Az are now functions of x comma y comma z, right? So Ax, Ay, Az you can say are scalar fields, right? Because they are real valued and they change depending on the location x comma y comma z, right? So a vector field is actually a combination of three scalar fields, right? Ax, Ay and Az, because each Ax, Ay, Az can be allowed to vary with x comma y comma z, right? So we'll look at some operations that we can do with vectors. The first thing is a simple scalar multiplication. So let's take the same vector A, and when I multiply it with the scalar k, I essentially get right. So the magnitude scales by k, and the direction remains the same, right? Right. So this is the scalar multiplication. So the next is the rules of summation with other vectors. So if I have a second vector b given by bx ex plus by ey plus bz ez, then I can add or subtract these vectors by just looking at their individual components and adding or subtracting them. right? So I essentially have to execute a component by component addition or subtraction. Okay, then we have multiplication. And in here we have two varieties, right? One is the scalar or the dot product, which is represented as A dot B, right? So I take two vectors A and B, and when I take the dot product, I actually get a scalar, which is equal to AX BX plus AY BY plus AZ BZ. Right? So this is a scalar number, right? So AX, AY, AZ, BX, BY, BZ are all scalar numbers. I essentially do component wise multiplication and then sum all three, right? So there are some interesting properties with regard to the scalar product, right? So when the vectors A and B are perpendicular to each other, we can show that A dot B is 0, right? And you can also see that the operation is commutative, which is I can swap or rearrange B and A, right, in A dot B. So we can say that A dot B is equal to B dot A, right? And when they are perpendicular to each other, it is equal to 0, right? And one way of sort of extracting the individual components of a particular vector is essentially to exploit this property, right? So remember that the unit vectors in each coordinate system have a unit magnitude and are mutually perpendicular to each other, right? So you can say that if I take the dot product of the vector with each of the unit vectors, I essentially get the component, right, along that particular unit vector. So if I need the component, the y component of the vector A, all I have to do is just get a dot product with the unit vector along the direction in which you would like to extract the component value of A, right? So I can essentially write these relations where A, when it's when you take the dot product with the unit vectors Ex, Ey, Ez, gives us the components, the respective components Ax, Ay and Az, scalar numbers, right? So that means to say when you look at these closed contour integrals, right? Remember you would have seen expressions like A dot ds, right? Say a closed loop, or it could be an open loop integral where S is some path, right? And ds is a small element, right, along the path. And this integral, and you have the integrand which is A dot ds, and if A were pointing arbitrarily in some direction, this A dot ds, right, the dot product between the vector and the line element ds is essentially asking the question how much of the vector is aligned in the direction of ds, right. So if I were to project the vector A along the direction of ds and then asked what this length is, that would be A dot ds, right. So hopefully you carry this idea or notion of scalar or dot product, right, back to all the relations that you saw in your high school, right, and sort of see now the relationships in a in this light, right, that you are essentially, when you take a dot product, you are getting the component, right, or how much of the vector is aligned toward the direction of choice, right. So dot product is very handy and becomes very useful whenever I need to answer this question of how much of the vector is aligned in a certain direction, right. So the second kind of multiplication you can do is the vector or the cross product. Okay, and that is defined as the determinant, right, of this arrangement of unit vectors and the scalar components, right. I would say that this is not typical, okay, to combine vectors and scalars in a matrix, right. So it should be clear to you that perhaps this is often advocated or printed in textbooks just in the interest of, you know, perhaps giving us a mnemonic to remember, right, what the what the cross product is, right. So we use the same principles of finding the determinant of a 3 by 3 matrix, right. So you can write this as ay minus bz, sorry, ay bz minus az by, right, gives us the x component of the vector, right. So the vector or the cross product takes two vectors and maps it to the vector space itself, right, whereas the scalar or the dot product takes two vectors and maps it to a scalar number, right. Then we have az bx minus ax bz and finally ax by minus ay bx dz. Okay, so rather than having to remember this, right, this seems a lot more easier to remember, right. So I just line up all the unit vectors on the first row, and then you have the individual components of the vectors a and b, and then when I try to expand it out as a determinant of a matrix, I can essentially get the final vector. Okay, all right, some properties of the vector product. If I were to exchange the locations of b and a in this cross product expression, we actually find that the magnitude of the vector stays the same, but the direction is the opposite direction, right? So you can say that A cross B is minus of B cross A. And you can also say that the vector A cross B, right? So you get an output vector, right? If you want to call this, say, C, right? Vector C is actually perpendicular to both A and B. Right? So A and B are two vectors, and these two vectors can determine a plane, right? So just like how 2 points can define a line, 3 points can define a plane. So if I were to take two vectors A and B, and if the tail end of these vectors are joined, and if I were to consider the 3 points, the tail end and the two head ends of the two vectors, I essentially get the 3 points, and these 3 points define a plane or a surface, and the product A cross B is essentially a vector that is perpendicular to this plane, right? So in the case of the rectangular coordinate systems, if I look at the unit vectors Ex and Ey, if I take the cross product in the order of the ordered triplet Ex, Ey, Ez, if I took the cross product of Ex and Ey, I essentially get Ez, right? Similarly, if I preserve the order, Ey, Ez gives me Ex, and Ez, Ex is plus Ey, right? So if I take any the two of the unit vectors and take the cross product, I essentially get the third, but remember that I have to preserve the order, right? So xy gives me z, yz gives me x, and zx gives me y, right? So as long as you maintain this order, but remember, if you just were to swap this order, you will only get a minus sign.